Okay, don't forget to click in, quick. All right, so let's see what the display shows now. If it's all A now. Got it. Oh, good, excellent, perfect. And two jokers again. And so the solution is this was here. I pointed it to you in the morning. I even didn't point to it. P is h over lambda, and h is a constant. So you will have P is h over 0.06 is this here, and what is P here? Is h over 600. P is what? Stands for what? Okay, so you would have to have 10,000 of those to get there. Okay, and this is the answer. Good. Now let's do it again because most is nice. Let's think about momentum one more time. So the kinetic energy is 1/2 mv, and P, the momentum is 1/2 mv squared. Sorry, and P, the momentum is m times v. Okay, so if I multiply this in here, I get P squared over 2m. You can do this yourself. Okay, you get P squared over 2m. So, and you have an electron. The mass is always the same. Okay, this will make no difference. So the relationship between this and that is actually what you need. And so we have electrons with a wavelength of 4 nanometers. We heat them 4 times to their kinetic energy. So this goes up by 4. What is the new lambda? What is the new lambda? Is it 1 nanometer, 2 nanometers, or 8 nanometers? So one you can exclude right away because you look at the wavelengths and you need to look at the energy. So if you heat something up, the energy has to increase. Okay, so one is eliminated right away. Okay, which one is the question, of course? Why don't you think about it and give me your answer? So you need to practice a little bit with this, okay? That you get the arithmetic down there. So there's actually 3 equations that you need to know, maybe 4. But actually, we give you the equations in the front of your midterm and final level. Most equations will be there. So. How come that you're not always clicking in here? Sometimes there are more, sometimes less, and you need to click in every time to get your bonus points. No, participation points. Okay, let's see. Yeah, ambivalent a little bit. So that's the good point. That's how we learn. So it's 8. You can't, if you have heated, you make the energy higher. Is that right? Okay, takes up energy. So which one can you exclude? If this is 4 nanometer, can you exclude this one? Okay, because it's less energy. Okay, all right. That's wavelengths. It's reciprocal to the frequency. So now you have, this is your relationship. Now if you quadruple this here, what happens to the wavelengths? Why don't you think about this again? And discuss it with each other, please. You also need to look at that relationship here. Well, what happens to the momentum? If you 4 times the energy, how much times the momentum goes? Okay, and now put it in here, in that equation. Put it in that equation. Yeah, fine, you can use that one too. Or use that one. It's the same here. Okay, let's see. Yes, excellent. Very good, very good. I like it. Very good. So now you don't know how you got there, I will explain it to you. So, of course, the first thing you did right is you see, that has to be smaller in wavelengths. It could be this or that. Yeah? But we have that relationship. The kinetic energy is directly proportional to P squared. Okay? If you multiply this with 4, what does P? You multiply P with what? No, that's to the square here. You multiply P with 2, the momentum double. You have to double the momentum if the energy quadruples. Yeah? Okay? Now if you double the momentum, what does this do to the wavelength? Makes it smaller by what? You double the momentum, makes the wavelength half of it. Okay, let's look at this here. There it is. This you can't forget this. These are constants. Okay, this is what you should learn. You don't calculate this stuff. Think it through. You know. And so 4 times the kinetic energy is 2 times P squared is 4. Okay, and with this you have lambda is h over P, so it's 1/2 of that, which is 4 over half is 2. Okay, 4 divided by 2. 1/2 of 4 is 2 to be more accurate. So we know now that waves. We know lots about waves, but we also know, because I told you so, electrons also behave as waves. And now we're going to think about this, conceptualize this, how a wave looks like, and how it would look like traveling around, and if I'm in nucleus, how it travels around the nucleus. Okay? So it has to be a standing wave. That wave has to stand around the nucleus. It needs to be around the nucleus. These are standing waves. They have to somehow come together. But I can't make a circle of waves here for you, but we can have a standing wave demonstrated here. Did you have a good lunch? No? Because it's very tough work here. That's rope-a-dope, we call this here. And what we have, this is going to be our wave. Okay? So this is not a wave. That's a piece of, what is it? Rope. Okay? So, but we say, in order that, we call it boundary conditions. We say, this wave has to go through 0 here, and it has to go through 0 over there where Karen holds it. So that if I put it together, if I take it off and put it together, then it's a standing wave, a continuous standing wave. That's why the boundary condition is 0 here and 0 here. They have to fit together. Okay? So now, this is not a wave. Let's put the smallest possible wave on there, please. How many wavelengths is this? It's a half wavelength. You only have a lobe. One lobe. Positive lobe, negative lobe. Positive, negative, positive, negative. 0 here, 0 there. Now let's put a whole wavelength on there. So what should you see? One lobe here and one lobe there. It should go through 0 here. One wavelength. One wavelength. Only one wavelength. There it is. It goes through 0 here. You see it stands here. it's positive, negative lobe here, positive, negative lobe here. Okay, that's a node here. We call this a node. Now let's put another wavelength on there. Sorry, Karen. Very hard work. Oh, wow, look at that. There's one. This is two complete waves, isn't it? One lobe, two lobes, one node, another one. So we have how many nodes do we see here? Two wavelengths? 1, 2, 3. Okay, and the two on the sides. There's two complete wavelengths. What can you do? What's the maximum? Okay, so you understand that we have nodes where they always are zero, the wave function, and we have lobes where they go up and down, up and down. They can be positive nodes, positive lobes, or negative lobes. Okay, positive or negative. And the nodes goes to zero, and our boundary condition is it has to go through zero there. Because if it doesn't go to zero here, it has to fit each other. It has to go around the wave. Otherwise, it would leave the atom, our electron. It has to be around the atom, so it has to meet up with each other. And I will show you in a second how this works. So thank you, Karen. We're done. At least that's what I think. So that you've seen, when I have the rope still, that's not a wave. The lowest possible wave I can have is 1/2 lobe. That's the lowest possible energy a wave can have. That we call the ground state, the lowest possible state, but it doesn't have zero energy. It has a fixed energy, and that energy is specific for each different atom and different electron, of course, but we get to this. So we have a ground state, and we plot the energy here. The energy increases from here to here, and this is just the population here. So that was this. Our wave function looked like this. One lobe, and that lobe was going from positive to negative, positive to negative, positive. Zero here, because that's what we said it has to be. Okay. Now the next one, we can say the energy. We plot this. This is our energy level. That's the energy level 1. That's the lowest possible energy level is 1. Okay. So n is the multiple, is a whole number. Remember, delta E was delta n times h times nu. So n is that number. Can be 1, 2, 3, 4, 5, 6, 7, and you will understand in a minute. So there was no node. Now the next one, the next higher possible state, you see that there was nothing else in between. We couldn't do anything else. The energy is higher of this. Of course, we had two half lobes, the full wavelength, and it had positive here, then it was negative, and this was negative here or positive here. Up and down, and there was our node. So our energy is higher. It would be here, our energy. Again, if you plot here energy, that would be quantum number 2, level 2. We call this level 2, and we have one node. Now let's put the next one in. What would the next higher level be? How many wavelengths would you have there? 1.5. Okay. 1.5 wavelengths. There you go. Has two lobes, positive and one negative, or two negative and one positive. Goes up and down, up and down. So how many nodes we have here? 1, 2 nodes. This one we take for granted. 2 nodes. And this is higher energy, and n equals 3. It comes in whole number multiples of half a wavelength. You see that? And so we have 2 nodes. What you see now, the more nodes you have, the higher the energy. And you see this is quantized. There's nothing in between. There's a level 1. You can go from level 1 to 2, or you can go from level 1 to 3. If you would have done it right away, she started at level 1, and then she goes to 3, and you can go on and on and on, okay? To level 5 million. Not really, but you could. But that would be also, the nodes would be increasing. So the first thing you learn is the number of nodes obviously is a measure for the energy, okay, of that wave. So there it is. You have to have whole numbers. You see, if I wouldn't have had this go to 0 and this was this end here, and there was that end here, if it doesn't go to 0, I never can have a standing wave around the nucleus. So now this is a very simple standing wave. This was n equals 4. So how many full n times 1/2? 4 times half is 2 full wavelengths I have on there. All right, supposedly. And yeah, I do actually. And so, see, that's how it stays around the nucleus, because it's a standing wave, n by 5 and 6 and so on and so on. And the question you could ask is, why doesn't that electron fall into the nucleus? Because the electron is negative. I taught you that the nucleus is positively charged. Why does the nucleus swallow up that electron? Because it's quantized. It can't do it. Quantum mechanics doesn't allow it. That's why it doesn't happen. Why it doesn't happen, and we explained it with quantum mechanics. Let's put it that way. And so, so the lowest energy state is still an energy state, is 1. And it's not zero energy, because you have half a wavelength on there. So understand it. The way the electron can have never zero energy around that electron, around the nucleus. Let me see if you understand. Or let me first explain a little bit more. Now, if you have absorption of light, and let's say we shine monochromatic light on this, okay? And I do this now in slow motion for you. So these are energy spacings, aren't they? These are H, this is the high energy, that's the low energy, the low energy, the low energy. So it's a delta E between this energy and 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 this energy. It's a fixed number. So it has to be a very specific energy. That wave of your light, only certain wavelengths will be absorbed, because the other ones won't fit in here. So now let's absorb this light. We shine white light, and let's see, this is our electronic system here. Doesn't do anything, because this is too high energy. It doesn't fit in any of the spacing. It doesn't fit from here to here, doesn't fit from here to here, or from here to here, or from here to here. Doesn't fit, okay? Blue, very high energy. So it goes from the ground state, that electron, takes up that energy, and goes in state number 1, 2, 3, 4, in n equals 4. So the delta H is, the energy of this is H times the frequency of the blue light. Now let's see what else we can do. We are now getting to lower energy, isn't that right? When we are here, here's the highest energy, we're getting to lower energy, longer wavelengths. So now what we do, the next one would be maybe green. Doesn't work. Doesn't fit into our electronic scheme. But this green fit in there, so it was this wavelength, and this absorbs it then. It's missing in the spectrum, because it has absorbed it. The energy that was in your light is taken up by your electronic system, or by your atom, the electrons of the atom. So the energy here would be, the change in energy is E times H times nu of the green light, the frequency of this green light. So what would be the next one? Yellow. Doesn't work. Doesn't fit. That's spacing, that's energy spacing. So now, red fits, and it absorbs it. So you see it's missing out of the light spectrum, because the energy was taken up by your electronic system. And you see here, the energy is, this energy of this is H times nu that energy. So you can calculate the energy between here and here, between here and here, between here and here, and the differences in between. Okay? Emission is the same thing. If something takes up energy, eventually it has to give it off again. All right? So now we have an emission. This is emission. It cannot land here. It cannot land in between here. It has to go to a defined state, to a quantum state for that atomic and electronic system. And so let's do it again. So now this is an emission spectrum. Emits that light. Now it also emits that light, and it emits that light. It can't emit any other light, because it has to go back to the ground state. No, you could have one emitting going from here to here, for example. So that would be a possibility. So let me ask you a question now. So you see, this is the energy spacing. This is increasing energy. These are the energy differences. And you get these emission spectrum. And this is our energy level, n equals 1, n equals 2, n equals 3. And this is our energy decrease and our energy increase, frequency increase. So which line arises when I go from here, from 3 to 1? Will it be line C, B, or A? Which one will it be? A, B, or C? If I go from level 3 to level 1. Think about it. So it comes back down. Will it have the highest energy or the lowest energy or something in between? Why don't you click in and then I close it and we discuss this the next time, but first let's see the result. My, we're getting more and more. Okay, I'm going to stop it now. Where did these people come from? Okay, let's see the result. Yes, you're getting it. Excellent. Have a good weekend. I see you on Monday.